So this is just going to be more practice with magnetic fields and magnetic forces and directions and stuff like that. And I think you'll find that the quiz will be somewhat like all of the things I've been going over. I don't want to throw anything. I don't want to throw you any curves at this point since there's no retake on the last quiz. So let's all get the last quiz exactly right. All right, so first problem found from these are just all little quiz problems. Yeah. Okay, so again, our magnetic field model. The way we deal with magnetic fields is that moving electric charges produce a magnetic field. Other moving electric charges feel that magnetic field. And although I don't think I'm going to ask you in this, there might be something on the final. So maybe I better add to that a little bit. It says up here, moving electric charges produce a magnetic field. If you remember, we had electric charges, whether they're moving or not, produce an electric field. And now you've had something added to that, which is that a changing magnetic field, a magnetic field that changes with time, causes an electric field. So that you saw that with Lenz's law, the magnetic flux through a loop. If it changes with time, then there will be an electric field around that loop that causes current to flow. So we've added to step number 1 a little bit and complicated it a little bit. I don't know right now whether anything like that will be on the final. Maybe by next week I'll be able to tell you that. But changing electric field produces a magnetic field also, and a changing magnetic field that changes in time, produces an electric field. So that's just a side issue, because this is still about the simpler version. Moving electric charges produce a magnetic field. Moving electric charges feel that magnetic field. So the first problem, current is a current of 4 amps flowing through a wire into the page. As this cross means there's a current into the page, a long straight wire that comes from out of the page, goes through the page and into the screen and into the screen. A charge of a -2, well, at one point it says microcoulombs, at the other point it says coulombs. Either one. At this point, if it were a real quiz, I'd have to fix that. Is 4 centimeters away from the wire, moving to the right with a velocity of 6 meters per second, as shown. Find the magnetic field at the location of the particle, the magnetic force on the charge. In which direction might the particle move so that the magnetic force on it was 0? That's kind of 3 questions. Probably on this exam was an equation, and I'm trying to remember the equation. I'm pretty sure that's what it will be for the magnitude of a magnetic field due to a long straight wire, because it says find the magnetic field at the location of the particle. You'll need to know the magnitude and the direction, and so I think that's enough equations, and you know right-hand rules, so I'll let you take a few minutes to work that out, and then we'll talk about it. Okay. So step 1 here, or find. The first thing it asks you to find, the magnetic field at the location of the particle. Magnetic field is a vector field. So the magnetic field at the location of the particle means find a vector, magnitude and direction, that represents the magnetic field at that particular location, the magnetic field due to the current that's moving. I mean, there is another charge moving. That negative charge is also moving, but it doesn't produce a magnetic field at its own location. So you don't have to worry in working this kind of problem. You always want to separate the charges that are producing the field from which you're interested in from the charges that are feeling that field, and that negative charge is the one feeling the field. So right-hand rule. If you're looking at this current directly in the direction of the current, so into the screen, the magnetic field circles around it, and the right-hand rule tells you whether that's clockwise or counterclockwise. With your thumb in this direction of here, I think you'll find that you're circling around clockwise, so that the magnetic field due to that, I don't want to make it look like it's the same kind of vector as the velocity. I don't want to even compare them, but I'm going to draw a magnetic field vector at Q at that point, which, if this circles around clockwise, when you're over to the right at it, the magnetic field vector points down. And the magnitude of that magnetic field vector is given by this, mu0, which is a constant that would have to be on the quiz. The current is 4 amps. And R is the distance away from the wire. And so R is 4 centimeters. So 0.04 meters. Make sure to keep everything in SI units so that the magnetic field ends up in a reasonable unit. So magnitude of the magnetic field you get by calculating the direction you get from a right-hand rule. So what's the direction of the force on the particle? Well, another right-hand rule. So what do you think? Out of the page? Thumb pointing in the direction of the velocity. Fingers, at least the John Conway version, hand outstretched, thumb pointing in the direction of the velocity, fingers pointing downward because the magnetic field is down the page, would have my palm pointing into the screen, but it's a negative charge, so out of the screen. So Q is a negative 2 microcoulombs, and so you end up with a force out of the screen. Using the, what I'll probably give you on the quiz is the thumb, index finger, and middle finger all perpendicular to each other. And so velocity to your right on the screen, magnetic field down, index finger points into the screen. Again, negative charge, so out of the screen. And so force, the particle it's moving to the right, and it's being bent by the magnetic field toward you, out of the page. Magnitude of the magnetic field, of the force by the magnetic field, well, it's just given by this. Once you know what B is, because you've calculated it here, you know what V is, you know what Q is, the sine of theta is 1 because V and B are perpendicular to each other. And so that'll give you the magnetic force. Calculate that, and it's a force out of the page. So I didn't quite ask you this last time. I mean, I mentioned it, but what what direction could the particle be moving so that the magnetic force on it was 0?
Is the theta? Can you just show us where the theta would be on that diagram?
Theta is the angle between the velocity vector and the magnetic field vector. Those are the only two vectors in the problem. So how can you make the magnetic force 0? This says which direction could it be moving so that the magnetic force is 0. Well, there is a magnetic field, so you want the magnetic force to be 0. There is a magnetic field. That isn't 0. It says in what direction is it moving? Okay, so it has a velocity, so that can't be 0 either. And the charge isn't 0. It certainly has a negative charge. And so the only thing you have left is sine theta has got to be 0 if you want that to be true. So what direction could the velocity be so that sine theta is 0? Anyone have an answer for that one? Theta is the angle between the particle velocity direction and the magnetic field direction. The magnetic field at this particle happens to be straight down. And so what direction should the velocity be so that there's no force on that particle? Down? Down works. Then the velocity and the magnetic field are in the same direction. So 0 angle, sine of 0 is 0. There's actually one other direction that works. Up. Up works too. Sine of 180 degrees, also 0. So if a particle is moving along the direction of a field line, then you will not get a force, a magnetic force, on that particle. It has to be moving at least a little bit perpendicular to that magnetic field line to have a magnetic force. Any questions about that? Positively charged particle is moving to the right near 3 wires shown in the picture. The 3 wires carry the currents in directions shown with equal magnitudes. So here are the 3 wires. I1, current this way. I2, current straight down. And I3 is a wire that's into or out of the page, and the current is coming out of the page. So those are all those 3 wires. Here's the particle with a charge. It looks like plus Q. I'm just going to tell you it's a positive charge. I clipped this out of an old quiz, and the charge is slightly obscured here, but I can see that it's plus, so I'm thinking it's plus Q. Here's the particle right here. The particle is the same distance from I2 as it is from I3, and it's twice as far from I1 as it is from the other 2. So, draw 3 arrows representing the forces by the 3 wires on the particle. If any of those forces are 0, just say they're 0. F by I1 on particle equals 0 or something like that, if it is. And then rank the forces from largest to smallest with an explanation. So, talk about it all you want. All right, so the very first thing you have to do in figuring out the force is step 1 up here. I mean, what's the direction of the magnetic field? So I'm going to do them in reverse order for some reason that I don't know yet, but maybe you don't. Maybe we both actually do know. I'm going to do I3 first. I3 is a wire perpendicular to the page. What's the direction of the magnetic field up above I3, so at the location of the charge? Direction of the magnetic field due to I3. Everybody point in some direction and tell me what you think that magnetic field direction is at that point. It's magnetic. It's the current coming out, so you know that the magnetic field circles around. Use your right-hand rule, your thumb pointing out, and you find out it circles counterclockwise around that wire. And so when you're up above, the magnetic field points how about this? Left or right? To the left or to the, it points to the left. It points to the left at the location of that charge. Circles around, right-hand rule tells you it circles counterclockwise, which means when you're up above it, it points to the left. If you were down below it, it would point to the right. What's the force on that charge due to that magnetic field? What's the direction of the force on that charge due to that magnetic field? 0. Why is it 0? Because it's actually it's parallel to the velocities. You might call it anti-parallel since they're in opposite directions. But parallel is a good enough word. Those two vectors are parallel to each other. They're opposite in direction, so the angle is 180 degrees, or pi, whichever you want to call it. And so that's what theta is, and so the sine of theta is 0. There's no force. Okay, so I don't have to draw that one. And so I'm sure this was done so that you wouldn't have too many arrows to draw. What's the direction of, in reverse order, we'll go to I2. What's the direction of the magnetic field at the positive charge due to I2? Left, right, up, down, into the page, out of the page. Out of the page. Everybody okay with out of the page? So magnetic field points out of the page. Positive charge is moving to the right. So force. What do you get for force? Up, down, left, right, into the page, out of the page. My thumb in the direction of the velocity. The magnetic field at that point is out of the page. Thumb in the direction of the velocity, magnetic field out of the page toward you. Force is down the page. F by I2 is down the page. What about I1? What's the direction of the magnetic field at that charge due to I1? Into the page? Okay, so the magnetic field points into the page due to I1. So what's the direction of the force? Magnetic field into the page, velocity to the right, force is up. Yeah?
How do we know that it's into the page?
Pardon me? How do we know?
That it's into the page.
So I1 over there has a magnetic field that circles around it. And so, let me see if I can do it on here. And so if the magnetic field circles around it, then when it's above the I1, it's either to the right or to the left. Your right-hand rule, if you point your thumb along I1, in the I1 direction, your fingers are curling up when you're over here on the right, and curling down if you're over here on the left. And so the magnetic field due to I1 is up when you're over here. When you're right above I1, it's pointing to the left. And when you're over here, it's anywhere over here, it's pointing down into the page. So it circles around I1, and your right-hand rule tells you that if you are looking at the current come at you, then it's counterclockwise. And so it's down into the page if you're in the plane of the wire and over here. In the plane of the wire and the particle. So into the page is the opposite of what you had before, and so the force is the opposite, and so it must be up the page. Is it bigger or smaller than the force by I2? Smaller. It's twice as far away, so it's half the force. Half the magnetic field and half the force. So if I were going to draw it, I would draw it smaller like that, force by I1. Yeah?
So for magnetic field, it's half because the R isn't squared, and for electric field,
because the R isn't squared. That's right. Yeah. Because it drops off away from a straight wire as 1 over R. It's only a straight wire that has that simple 1 over R shape. Or form. So rank the forces largest to smallest in magnitude. Force by I2 is the largest, then force by I1, and then force by I3, which was 0, so that's the smallest. Any questions about that one? All right, now I'm going to ask you to think in 3 dimensions. You kind of always have to think in 3 dimensions anyway for magnetic fields because, I mean, that's what these 3 fingers do for you. They point it all in 3 different directions. The right-hand rule gives you is for 3 dimensions. So it can get a little complicated. I'm trying to make this clear. So how does an electric motor work? Well, you probably know that with an electric motor, you either need a battery or you plug it into the wall. And so one way or another, something is causing a current to flow in an electric motor. So what I'm showing you here is a loop, a wire loop. There's 2 pictures of a wire loop. On the left, the wire loop has a current which circles around the loop clockwise if you're looking at it from above. So if you're looking at it, if you're looking down, maybe I'll get rid of these pictures and draw a top view of that. Top view of the one on the left looks something like that. Your current goes around the loop clockwise, and from a top view, the magnetic field lines are coming at you. And it's a uniform magnetic field. So the magnetic field lines are all coming at you, so they would look like that from a top view. So that's what that picture is meant to be. Magnetic field, current. How does an electric motor work? You put current through a loop, really not just a single loop. Usually you make a whole bunch of coils, hundreds of loops. You open up a magnetic motor, you'll see a bunch of coils over and over, tiny little wire. But here we're just showing one loop. And you put it in a magnetic field. So electric motors generally have magnetic fields. The other picture, you're kind of looking at the face of the loop in this view that the picture shows, that the problem shows. If I did a top view of that, the magnetic fields are still, magnetic field lines are all still pointing at you in this top view of this other one. But the loop just looks like that. From the top view, you're just looking down at the edge of the loop. So on the left view, on the left problem from the top, you're looking at the face of the loop, at the plane of the loop, and on the right, you're looking down at the edge of the loop. So that's what the picture is meant to show. Each show a loop of current in a uniform magnetic field B. In the picture on the left, the plane of the loop is perpendicular to B, so that's why you can see the loop on this picture I drew from the top view. In the picture on the right, the plane of the loop is parallel to B, so that's why when you're looking down the field, you just see a line. Suppose neither loop of current is moving in the picture. So that's what happens in an electric motor. You don't hook up an electric motor and it's already turning. You hook it up and it has to start to move. So there is a time before you're putting current through when it isn't moving. So suddenly you hook it up and put current through. Does it move or does it not? The question is which loop, if either, will start to rotate. So which loop is going to rotate here? And the way to decide that is to look at the direction of the loop is made up of 4 pieces, 4 sections. On each section, there will be a force, maybe. I mean, there's a current and a magnetic field, so reasonable to think there will be a force. In which one is there a net torque? A set of forces that cause it to rotate. So just do one section of the loop at a time and figure out the direction of the magnetic force. And then tell me if one, both, or neither of them starts to rotate. Give you a couple minutes to do all those right-hand rules. All right. So I suspect you've noticed, but you may not have really thought of it this way, that your right-hand rule always ensures that magnetic force is perpendicular to the velocity vector and perpendicular to the magnetic field. So there's a plane made up of the velocity vector and the magnetic field. That plane is perpendicular to the force. So if you look at this one on the left, there's the bottom here has a vector to the left, positive charge moving to the left. I'm going to say positive no matter what's really flowing. If the current's to the left, it's as if positive charge moved to the left. So positive charge moving to the left, so velocity to the left here in the bottom. And magnetic field vector is out of the plane, so toward you. And if the magnetic field vector is out of the plane and the velocity vector is to the left, then the plane that those make up is a vertical plane. You're looking at the cross-section of a vertical plane. And that means the magnetic force has to either be up the page or down the page. In this case, the right-hand rule, I think, tells you that the magnetic force is up the page for the bottom part. Twisting my hand around here. So the force here is that way, magnetic force. This current is going around, so the force here is going to, up at the top, is going to be the opposite. And so that magnetic field is trying to push those 2 wires together. What's it doing to the ones on the side? Well, the current is on the left side, the current is up the page, and the magnetic field is out of the page, and so I think you'll get a force to the right, I hope. Is that right? On the left-hand side, I think you'll get a magnetic force. I mean, on the right-hand side, I think you'll get a magnetic force to the left. So this magnetic field is trying to crush the loop, but it isn't trying to rotate. These forces are exactly equal and opposite to each other along the same lines. All of these forces are in the plane of the loop. If I want to rotate a loop around some axis that's in the plane of the loop, I can't have forces in the plane of the loop. Those won't give me any torque. Conversely, you can think about this one over here. Up at the top of the loop, let's see, if I look at the picture over here on the right, the bottom of the loop has the current going to the left. So the bottom of the loop has a magnetic force that's, I think you'll find, into the page. And if you look at the top view, that means the force on the bottom of the loop is pointing that way from a top view. Depends on how you're looking at the top, but I'm going to say that the top view looks like that. And then the force on the top piece has a current to the right, magnetic field is still up, and so the force on the top piece is out of the page. So the force on the top of the loop is out of the page. I hope you can see that if I push the bottom into the page right here and I pull the top out of the page, that I'm going to cause this to rotate around this axis. If I push the bottom into the page and pull that out of the page, then I'm going to rotate it around that axis right there. So the one on the right is the one that's going to start to rotate. The one on the left is not going to start to rotate. Any questions about that? So basically that's how an electric motor works. You got a loop of current and a magnetic field, and a loop of current and a magnetic field can sometimes rotate or be forced to rotate. Another way to think about this, I guess, is that this loop of current is a magnetic dipole. It's a magnetic dipole, and if you use your right-hand rule, I think you'll find that magnetic field due to this loop of current is going in the center of the current is going into the page. So the loop of current itself, let me get rid of all this other junk for a second. The loop of current itself, from a top view, is a magnetic dipole. It has magnetic field that comes out of from a top view, it comes out of this side. That would be out of the back if you're over here on this view. Goes into the front and out of the back, the magnetic field lines. And that means behind this loop is a north magnetic pole, and in front of this loop is a south magnetic pole. And you already know that if there's a dipole with a north here and a south there, and the magnetic field that's applied is out of the plane of this, it's this magnetic field, this is the applied magnetic field. You already know, I think, that dipoles want to point along the field. So this north wants to rotate upward from a top view. This north wants to rotate the north wants to rotate so that it's pointing along the magnetic field with the south on the other side. So that way of thinking about it gives you the same answer as we got just by thinking of the forces. That it wants to start, that this one will start to rotate. On the other hand, this loop of current has a magnetic moment, a dipole moment, that points in the same direction as the magnetic field. So it points opposite to the magnetic field. So it is exactly opposite to the magnetic field, so it doesn't have a torque on it. With this one on the left, if you just hit it a little bit, suddenly it would want to flip over because it's pointing in the wrong direction. This one on the left has its north, this loop of current has its north pole on the other side. From this top view, the north pole is on the bottom, and the magnetic field points out of the page, and so it would like to be exactly opposite. It would like to flip over. And I don't know if you've ever plugged in a battery in an electric motor. Sometimes you plug it in and it doesn't move. But if you just kick it a little bit, it will start to move. And this is the kind of situation when there's no torque on it, but if you just kicked it a little bit, so you rotate it a little bit, then the dipole moment would try to flip over and point in the right direction. So if you've ever had that with an electric motor or a little electric car, and you plug it in, you turn it on, and it sits there and it doesn't move, and then you just tap it a tiny bit and it takes off. That is why it got, I mean, there's friction involved too, maybe, but one of the problems is that it could just be stuck in the wrong direction. And it's easy to get it out of that direction. Okay, any questions about this one? Different ways of looking at the same problem? All right, really quick one. Loop of current, circular loop of current. An electron is at the center of this loop, and that electron in the center of this loop has a velocity vector toward you. What's the direction of the force on the magnetic force on the electron? Exactly at the center. There's an electron whose velocity is moving out of the page. What's the direction of the magnetic field exactly at the center? Left, right, up, down, out of the page, into the page? What cancels out? Is there a magnetic field exactly at the center? And if there is, what's the direction? So I get into the page. Everybody okay with that? Directly into the page. The electron moving directly out of the page. What's the force on it? 0. This was obviously a trick question. There is no magnetic force on that electron because the angle here is 180 degrees.